to the Geomaster class, where we make geography simple, exciting, and easy to master. I am your guide to unlocking the world one theme at a time. Let's jump into today's topic. So today we are focusing on mid-latitude cyclones. So a mid-latitude cyclone is a large low-pressure weather system that consists of fronts. It forms in the mid-latitude between 30 and 60 degrees north and south of the equator. So there may be different names for mid-latitude cyclones. They may be called temperate cyclones or frontal depressions or even extratropical cyclones. But these weather systems bring a variety of weather, including rain, snow, and strong winds, and also temperature changes. So our lesson coverage for this lesson will be focusing on the origin of cyclones, followed by the general characteristics, not forgetting the conditions that are necessary for the formation of tropical cyclone, of mid-latitude cyclones, So we'll also look at the stages of formation of mid-latitude cyclones. Then we'll also lastly interpret the cross-section of a mid-latitude cyclone. So mid-latitude cyclones originate at the polar front, where warm tropical air converges with cold polar air. This clash of air masses creates instability, setting the stage for the development of these powerful weather systems. By understanding their origin, we unlock the key to know how they form. Knowing the starting point helps us predict their movement and intensity. We are also able to tell why they behave the way they do. The interaction between warm and cold air explain why these cyclones bring diverse weather patterns in terms of rain, wind, and temperature changes. And it also makes us to connect to the bigger picture. It connects global air circulation and helps explain larger climate systems. So it's like building a house without understanding the foundation. The rest doesn't make sense. Understanding their origin gives us the context to explore their structure, movement, and impact on weather and daily life. So, mid-latitude cyclones are one of the most significant weather phenomena, affecting regions between 30 and 60 degrees latitude. So, let us explore their key characteristics. Mid-latitude cyclones form between 30 and 60 degrees north and south of the equator. Unlike tropical cyclones, which move westward, the mid-latitude cyclones are driven by the westerlies, meaning they travel from east to where? They travel from west to east. So this explains why weather systems in South Africa and many other mid-latitude regions often move in an easterly direction. So, a key feature of mid-latitude cyclones is that they consist of two main fronts, a warm front and a cold front. These fronts develop because of that clash between the warm tropical air and cold polar air. So this interaction creates instability, leading to different types of rainfall and changing weather conditions. In terms of size and duration, we know that these cyclones are not just small storms. In fact, they can be over 3,000 kilometers in diameter, covering vast areas. Because of their size, their impact can be felt over multiple days, typically lasting between 4 to 14 days before dissipating or moving away. So, lastly, mid-latitude cyclones occur throughout the year, but in South Africa, they are most active in winter, so they bring winter rainfall. This is because colder temperatures intensify the contrast between warm and cold air masses, making the systems stronger. Understanding these characteristics helps us predict and prepare for the weather changes they bring, from cold fronts bringing rain to sudden temperature drops. Mid-latitude cyclones play a crucial role in shaping our daily weather and long-term climate patterns. So, these massive weather systems don't just appear out of nowhere. Specific conditions must be in place for them to develop. Let's break down the key factors that set the stage for their formation. Firstly, we have the presence of the polar front. Mid-latitude cyclones form along the polar front, which is the boundary where cold polar air converges or meets the warm tropical air. So as already mentioned, that this clash between the air masses creates instability, setting the foundation for cyclone development. So a strong temperature contrast between the cold and warm air is also essential. That means a strong temperature gradient is crucial for the development of mid-latitude cyclones. So the greater the difference in temperature, the more energy is available to fuel the cyclone, making it more intense. There must be also the Coriolis force. The Earth's rotation causes moving air to be deflected due to Coriolis force. This deflection is what gives the cyclone its characteristic rotating motion, with winds circulating counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Moisture also plays a crucial role in cyclone development. When warm, moist air rises, it cools and condenses, releasing latent heat. So this heat adds more energy to the system, intensifying the cyclone and increasing cloud formation and precipitation. So for a cyclone to develop, there needs to be initial disturbance, which is the trigger mechanism, such as a ripple or wave in the polar front. This disturbance helps to kickstart the spinning motion of the system. Then there must be also frictional drag. Near the surface, friction with land or ocean influences wind patterns. This frictional drag shapes the movement of air, guiding the cyclone's development and affecting wind speeds. So these vectors work together to create mid-latitude cyclones, which are responsible much of the weather we experience in mid-latitude cyclones like South Africa. Without them, these powerful systems wouldn't exist. Now that we understand how they form, we can predict their behavior and impacts. Now, before we look at the stages of formation of mid-latitude cyclone, let us quickly look at the concept of cyclogenesis, which is a process by which a cyclone forms and develops in the atmosphere. It involves the intensification of a low-pressure system, leading to the formation of strong winds, cloud development, and precipitation. Understanding cyclogenesis is crucial for predicting weather patterns, especially in mid-latitude regions like South Africa, where these systems bring significant winter rainfall and temperature changes. So, the first stage of development of a mid-latitude cyclone is the initial stage. So, during the initial stage, warm tropical air from 30 degrees north and south of the equator and cold polar air from 90 degrees meet or converge at the polar front. But the Coriolis force now deflects both air masses, whether it's occurring in the southern hemisphere or in the northern hemisphere. If it's in the southern hemisphere, the Coriolis force deflects both winds to the left. If it's in the northern hemisphere, the Coriolis force deflects the winds to the right. For example, in these two diagrams that you are looking at, they are occurring in the northern hemisphere because the winds are deflected to the right. After the initial stage, the cyclone develops to a wave stage. So the wave stage occurs when frictional drag takes place between the two air masses. Then a wedge of warm air begins to be uplifted by the cold air. Fronts begin to develop as the air converges in a clockwise direction in the southern hemisphere and anti-clockwise circulation in the northern hemisphere. You can see here that both of these diagrams again are the formation of the mid-latitude cyclones in the northern hemisphere. As you can see that the air circulation is anti-clockwise around the low pressure. Next, after the wave stage, the cyclone develops to its mature stage. So the wave deepens or intensifies and isobars at the flanks kink and point away from the low pressure. The cold and warm fronts and sectors are fully developed in a well V-shaped. That is how we will identify that the mid-latitude cyclone is in its mature state. You will see that the cold front and warm front are fully developed, and it has a well-formed V-shape. Cooling, condensation, and cloud formation are associated with the rising air. So that cold, dense air uplift the warm air, leading to rapid rising and condensation of that warm air mass. So the cold front is associated with towering cumulonimbus clouds, and the warm front with a broad band of stratus or nimbostratus clouds. Lastly, we have the occlusion stage. So this stage is reached when the cold front catches up with the warm front at the apex, because the cold air is heavy and dense, so it moves faster than the warm air. Occlusion starts at the apex because it is the shortest distance between the two fronts. So an occlusion can be either a warm or a cold front occlusion. So as the cold front continues advancing on warm front, the occlusion increases progressively, removing the warm moist air from the center of the low pressure system. Right. Then we have the cold front occlusion. You must know the difference between the warm and cold front occlusion. So here's the difference. Firstly, the cold front occlusion takes place when the coldest air is found behind the cold front, and this causes the warm air to be uplifted along the cold front. Then the cold front undercuts the warm front. Then a cold front occlusion occurs. Then a warm front occlusion takes place when the coldest air is found ahead, not behind, ahead of the warm front. That means in front of the warm front, and this causes the cold air to be uplifted along the warm front. Now, without the warm air mass to maintain it, the low pressure system gradually dissipates. In other words, when all the warm air mass has been uplifted, the cyclone is in the dissipating or degenerating stage. So those are the 4 stages of development of a mid-latitude cyclone that you must master. A mid-latitude cyclone is more than just a swelling system on a weather map. To understand how it works, we need to examine what happens inside. That means let us look at the cross section of a mid-latitude cyclone. Firstly, mid-latitude cyclones typically move from where? From west to east in mid-latitudes because they are driven by the prevailing westerlies. That's the general direction. Then let us put our focus on the cold front first on the left of the screen. So the cold front is located at the leading edge of the cold air mass, where the cold air advances and displaces the warm air in the warm sector, as you can see in the diagram. So the associated weather conditions of the cold front is that there is a presence of cumulonimbus clouds, will indicate the intense or the rapid rising of warm moist air leading to condensation, and then that condensation leading to heavy precipitation and thunderstorms in front of the cold front. And sometimes there may be severe weather such as hail and strong winds. In terms of temperature, as the cold front passes, the temperatures drop sharply. The winds typically shift from southerly to northwesterly as the front passes, and we are still speaking about the cold front alone. Now let us look at the cold sector. The cold sector is the region behind the cold front, dominated by cold air, because all the warm moisture has been uplifted. So the weather conditions that are experienced there, the air is generally cool and dry, with a clear or partly cloudy skies. The atmosphere is more stable, leading to less vertical motion and reduced precipitation. That is the conditions experienced in the cold sector behind the cold front. Now let us look at the warm front. So the warm front is located at the leading edge of the warm air mass, where the warm air advances and overrides colder air. So the weather conditions that are experienced along the warm front is associated with layered clouds such as stratus or nimbostratus, leading to prolonged light to moderate rainfall. The temperature, in terms of temperature, as the warm front passes, the temperatures gradually increase because it is accumulated by warm air. The winds typically shift from easterly to southerly as the front passes. Now let us look at the warm sector. The warm sector now is the region between the warm front and the cold front, dominated by warm, moist air. The weather conditions that are experienced in the warm sector, you'll find out the air is warm and humid with overcast skies and occasional light or drizzle. The atmosphere there can be unstable, especially near the cold front, leading to development of thunderstorms because of the rising of warm, moist air. So, just to summarize the whole concept of the whole weather conditions that are experienced in the mid-latitude cyclone, as we can see that they differ. Along the cold front, there is heavy precipitation, thunderstorms, the temperatures drop sharply, and the wind shift. In the cold sector, there are cool, dry, and stable weather conditions with clear skies. On the warm front, there is prolonged light to moderate precipitation with gradual temperature rise, and not forgetting the wind shift. In the warm sector, there is mild, humid, and unstable conditions with overcast skies and occasional light rain. So that's it for today. Thank you for joining me on GeoMasterclass, where we simplify the complex and bring geography to life. See you in the next lesson, which is the continuation of mid-latitude cyclones, whereby we'll be looking at the related weather conditions associated with cold, warm, and occluded fronts. We'll also look at the impacts on human activities, that means including social and economic, not forgetting the environment also. Then lastly, we'll look at the possible precautionary management strategies to mid-latitude cyclones. So if you find this video useful, don't forget to like, subscribe, and hit the notification bell so you never miss a lesson. And if you have any other questions or topics you'd like me to cover, drop them in the comments below.